Alright, now in the last video, we talked about the differentiation by first principle formula, and we discover that the dy dx, which is the gradient function, can be found by using this formula, such as limit of delta x tend to 0 of this function called f x plus delta x minus the fx divided by delta x. So this is essentially the rise overrun, okay, of the chord PQ from the previous video that we discussed earlier on. Alright, so this is the formula. So now I'm going to show you how we're going to use this formula to find the gradient function of a curve. Alright, now let's say we have a curve which is fx equals to x squared. So all of us knows that this is a curve, and therefore the gradient at every point on the curve is different because it being a curve, right? So, and let's say we are interested to find the gradient function. That means something like a machine to help us find the gradient at any point on the curve. Okay, how do we do that? Well, let's try to use this formula. Okay, so according to this formula, we need to first of all establish what is fx plus delta x. So it's not that difficult to understand that fx equals x squared, so fx plus delta x will naturally become x plus delta x bracket square, and therefore the dy dx, which is the gradient function that we are actually trying to find, will be equal to the limit of the delta x tend to 0, okay, of the f of x plus delta x, which is in this case x plus delta x bracket square, okay, and of course minus with fx, and our fx is actually the x squared itself, divided by delta x. Okay, so this is the formula, and this is how we're going to differentiate our fx. Alright, in terms of using the first principle. Alright, by the way, we should let y be equal to fx so that our dy dx will make sense. Okay, so let's move on, and how do we get the answer? Okay, so how do we work on from here, right? So let's copy the limit, and what we need to do is to expand out this perfect square that will give us our x squared plus 2x multiplied by delta x plus delta x square minus another x square over delta x. Okay, so those of you a little bit confused, let me help you out a little. Alright, now this expansion, when fully expanded, is will become these three terms. Okay, so this is your basic algebra formula, which you should have memorized by now very well, and you should be able to do this pretty fast as well. Okay, so let's move on. Alright, so limit of delta x tend to 0, and we need to simplify this, well, obviously, and it is pretty easy to see that this x squared and this x squared will be cancelled away. Okay, cancel off, so we got no more x squared, and what we left with will be 2x multiplied by delta x divided by delta x. So okay, maybe let me just write that down. Okay, so we ended up with something like this. Okay, and of course now what we need to figure out is what will happen to this entire thing. Okay, I don't know what to call this, but this entire limit if my delta x tend to 0. So of course we can simplify a little bit further. So we know that this, after simplifying, it becomes 2x plus delta x. And I think it's not that difficult for us to understand that if my delta x tend towards 0, that means this term here gets ever so close to 0. That means to say almost as good as 0, non-existence. The entire thing will be simply 2x. Okay, so this is the answer. This is the limit, okay, of this entire function here. So far so good. So in other words, we know that the dy dx is equal to 2x for x squared. What it means is that, well, this is the gradient function, okay, the gradient machine. So if I'm interested to find out the gradient at the point x equals to 1, all I need to do is to substitute in x equals to 1. Okay, if I'm interested to find out that the gradient at the point x equals to 2, I just have to substitute in x equals to 2 into this machine. Okay, now let's carry on and take a look at one more example, and we try to see if we can do this a little bit faster rather than to do these steps every time we need to differentiate. Okay, so let us now imagine that we have another curve which is y equals to fx equals to x cubed instead of x squared. All right, and again, our fx plus delta x will be then rewritten as be rewritten as x plus delta x bracket cube. Okay, and according to the formula that we discussed from the previous value and from the previous video, and as well as from here, this formula. All right, let us rewrite it. Okay, here. All right, such that it is the limit of delta x tend to 0, and this entire thing. Okay, so it's essentially the same as the previous example that we discussed, that we did here, over here on the left, except that it is now in cube rather than square. So let's try to find out what is the difference here and what do we end up with the answer. Okay, so after expansion, let's try to do it a little bit faster. Okay, so that we not to waste time doing all this not so interesting points. Okay, the more interesting points comes from behind. Okay, yeah, a little bit running out a little bit of space here. So I have another negative x cubed at the top. Okay, so let's just squeeze everything up here. Okay, and let's see where they become. Of course, for those of you who are not so familiar, let me guide you a little again. So this perfect cube can be expanded using a binomial theorem, and when it's fully expanded, you get these four terms here. Okay, this highlighted four terms here, which is the expansion of this. Okay, and of course the x cube being there all along is here. Okay, just like not enough space, as you can see. All right, so let's move on and let's try to simplify as what we did earlier on and see what we ended up with. Okay, so let's try to simplify this and do it a little bit faster. So we get x cubed. Um, oh, the x cubed and the x cubed will be cancelled away. So let me show you. This x cubed minus away this x cubed, there won't be any more x cubed. Okay, so that's the good news. All right, we've got no more x cubed, so we're only left with 1, 2, 3, three terms. So it's 3x squared delta x divided by delta x, then I got no more delta x. Okay, so it simply becomes 3x squared. Similarly, we have 3x delta x bracket square divided by a delta x. That gives me my 3x, and I'll be left with 1 delta x at the top. Okay, now this is delta x cubed divided by a delta x. That gives me a delta x square. All right, and I think again it's not that difficult for us to understand or imagine that if my delta x tend to 0, okay, that means to say this is as good as 0, well, then the entire thing is not really quite affected by this, isn't it? So you can throw it away. And if this delta x tends to be 0, as close as possible to 0, maybe 0.000001 or something like that, and when you multiply by 3x, the entire thing is as good as 0 as well. Okay, so that leaves us with the answer of 3x squared. All right, so this is how we differentiate our function using the first principle. Okay, now of course we try to see a pattern, because if every time we need to do some differentiation, we need to find a gradient of some curves, we need to do all these steps, it can be quite tedious, and that is only if we're talking about x squared and x cubed. How about when we talk about other functions, for example, like the exponential function, the ex, or for example, maybe x power 10, then we have a headache, right? We have a big problem, isn't it? Because we're going to expand it endlessly. So there must be a pattern, and there must be something that we can use from here. Okay, so let us take a closer look. All right, let's scroll down a little, but bearing in mind these answers that we need. Okay, so what we figure out so far is that if my y is equal to x squared, okay, and then my dy dx, which is the gradient function, will be given as 2x, which is what we found out here. And similarly, if my y is equal to x cubed, okay, and then my dy dx will be equals to 3x squared. All right, so if you go on and try x power 4, which is not a very good idea because of the binomial expansion. You can imagine the number of terms we have, right? So, but if you really go and do it, you will end up with 4x cubed. So, I want you to see that there is a very useful pattern that we can actually discover from here, and therefore we can use this idea, this way for us to differentiate differentiate x to the power 5 and x to the power 50 for that matter. Okay, and there is always a link between the power and the coefficient. Okay, you notice that the power 3 and there'll be a 3 here, the power 4 and there'll be 4 here. And similarly, the original power, that means to say in this case it was a power 2 and now it becomes power 1. Okay, it was a power 3 and now it becomes a power 2. It was a power 4 and now it becomes a power 3. So if this pattern were to hold, all right, we will be able to discover this formula that says if I have y equals x power n, then my dy dx will be equal to n multiplied by x to the power n minus 1, which is in congruence to all these results that we got here, isn't it? All right, so this is going to be one of the first formula that you are ever going to learn and memorize very, very well in your journey towards this chapter called calculus or differentiation. All right, so let us use this and proceed on with a few more results based on this. All right, so in general, if I have y equals to axn or ax power n, not to be mistaken with something else. So dy dx will be equal to a multiplied by n with the x with the power reduces by 1. Okay, which is the same as this discovery that we discussed earlier on. The only difference is that there's a coefficient a here. Okay, so far so good. So now we know all we need to do to differentiate is just to bring down the power. Okay, literally bring down the power multiplied by the coefficient in the front, and the original power reduces by 1. Okay, so let me demonstrate once to show you. If a equals to 10x squared or 10x cubed, okay, so without doing the first principle steps, I'll be able to figure out that the dy dx is actually 30x squared. Okay, 30 because the 3 is going to be brought down to multiply by the 10, and 3 multiplied by 10 gives me a 30, and the original power being 3 reduces by 1 gives me a 2. Okay, so a few more interesting results based on this. Let us talk about it as well, so that we are in good shape to go into the next example that we will show you. All right, so let's say I have y equals to ax. No axn, but ax. So my dy dx, okay, will be equal to, in this case, now the x actually has got power 1. Okay, but nobody writes the power 1, so it appears invisible. So imagine that there's a power 1 here, okay, nevertheless. So this power 1 is going to be brought down to multiply by a, and therefore we get a. And we get x, right? And the 1 that used to be there, I mean, it's supposed to be there, but it's invisible. All right, so 1 minus 1 will give us a power 0. And therefore, anything to the power of 0 is 1, isn't it? So therefore, we end up with a. So this is pretty interesting and pretty easy as well, and that is to say that if I have y equals to ax and I want to differentiate this ax, it becomes a. All right. Okay, so and that goes to say that if I have y equals to 10x, the dy dx, which is the gradient function, will be 10. Okay, and if I have y equals to 5x, and the gradient function will be dy dx will be equal to 5. So it's not that difficult to understand this or to master this really. Okay, so let us go on and understand this a little bit further. First of all, we all need to understand that y equal to 10x is not a curve. All right, it is a line. Y equals to 5x is not a curve either. So we're talking about a line, and based on the previous example, the previous video that we discussed earlier on, for a line, okay, the gradient, let's say this is a line y equal to 5x. Okay, the gradient at any point okay, on a line is the same. Okay, so the gradient is the same throughout. All right, it doesn't change like a curve does. So y equals to mx plus c, and we all know that mx plus c, the m, which is the coefficient of x, is actually the gradient of the line, isn't it? So therefore, as you can see, it goes well with this idea of differentiation, because when we differentiate, we get 5, and the 5 is actually the gradient here. Okay, so hopefully it makes a bit more sense to you. All right, so let's move on a little bit more to a last thing that we want to discuss, and that is if I have y equals to a, and I want to differentiate this, okay, dy dx. How do I do that? Okay, now you need to understand or imagine, you really got to try to use your imagination, that this a has got no x. Not true actually, because it actually has an x, but it's x power 0. Okay, that's what we see, what we saw here. A multiplied by x power 0 gives us a, because anything to the power 0 is 1, right? So when you have a, it simply means that there's a x power 0 behind somewhere. And if we were to differentiate this, you're going to bring down the 0 power down, and 0 multiplied by anything gives us a 0, isn't it? So there will be a 0. Now it doesn't matter that the x now will be a power negative 1, because 0 multiplied by anything gives us a 0. So there you go, it's a 0. Now what this implies is that if I have a constant term, let's say y equals to 5, and I want to find the gradient, which is the dy dx of 5, I will get 0. Okay, so in other words, I just differentiate any constant, it will become 0. And it goes well with the understanding that we have graphically as well, because y equals to 5 is again a straight line, it's not a curve at all. So a straight line, in fact, is a horizontal line, which looks a bit like this, y equals to 5. So if we are interested to find the gradient of this line, okay, and every point the gradient will be the same, it's a flat line. And remembering that gradient is actually a measurement of steepness, so being a flat line is not steep at all, and therefore the gradient is 0. Okay, so I hope everything makes a bit more sense, and everything actually starts from this differentiation by first principle. But of course, when we do our actual differentiation for our exercises and practice, we don't need to do this all the time unless the question specifically asks us to differentiate using the first principle. Otherwise, generally, most of the time, we'll be doing something like this, which is fast and easy. Okay?